All right, so we're still talking about these reading problems. So we're going through, I keep thinking I'm going to get it wrapped up in less videos, so sorry that this is your fourth video on 1.2, but I have a couple more things to tell you. I wanted to do one more example with the money question. So I always like for you to pause, try this on your own, get the right answer, and then you can kind of fast forward to the next one if you like. But here's how I would work this out. I'm more visual, so if I draw like money bags, I'm calling these sort of like the container idea when we were doing mixture. You're mixing two accounts trying to get a certain mix of interest income. Now on these, the interest income will always be listed as a total value. So $2,800 is what we're trying to get from the interest in this plus this account. Now to get interest, we multiply the principal times the rate times the time. Those are the three factors that multiply to give us interest in this account, then plus interest in that account. In the reading, you'll find those three values. So a church building fund has invested some money in two ways. So it doesn't tell me exactly how much in either one. Part of the money is at 3%. So I'm going to say 3%, and 4 times that much at 2.75%. So there's the percentages, and we assume that it's a 1 year. I don't know if it says it, but always assume time annual. There it is, annual income. So assume time is 1 year, so you really don't have to worry with it. It's just times 1. The principal and the rate are the two biggies. So notice that I don't know how much at 3%, and then 4 times that, which would be 4x, how I could express that at the 2.75%. So you multiply this stuff together, so 3% move 2 left makes 0.03 times x times 1. That's the interest in that first account. Same thing here, move 2 left to change your percent to a decimal, times 4x, or let's put a parenthesis, equals a total interest of $2,800. Now, if you want to, you would have to times by, what's that, 10,000 to move over 4 places. And then they'll all have to be times by 4 extra zeros, 10,000. So I probably wouldn't do that, just to be honest. I'd just work with the decimals, since that would make such huge values over there. You know, this one would have 4 extra zeros on it if we use that method. So that's optional and up to you. But I'm multiplying this right here, x term, 0.0275 times 4 equals 0.11, and then it has an x on it. Then I can combine these two x terms, they're like terms, and make it 0.03 plus 0.11 is 0.14. 0.14x equals 2,800. Then divide by what's with your variable, 0.14. That cancels that off. And then back to my calculator, 2,800 divided by 0.14 is 200. What's 200 mean? It means $200 invested at the 3%, and 4 times that amount, which would be 4 times 200, is $800 invested at 2.75 for your final answer. All right, the last topic in this 1.2 monster section is modeling. And in this application, we see one of the most used forms of algebra in the real world. Data is gathered and analyzed to see if a pattern or equation emerges. This is called modeling real data. If data can be modeled with an equation, then we can make future predictions. We might recall the models we heard so much about during COVID-19. The statisticians are in constant motion looking at numbers, analyzing our numbers, and then creating models to make predictions about if things continue as they are, what to expect. So model predictions. So if data can be modeled, this kind of leads us a little bit into statistics, but we're not going to go that far with it. We're just going to say, hey, they already modeled it. However they figured it out, here's the model or the equation they think they can base their predictions on. So we have an example here of it's healthcare expenditures in the U.S. where they have modeled what they think, an equation that predicts and defines the data. And it'll tell you in the reading, so the nice thing on these is you don't have to create an equation. They're already created for you. You just have to interpret them. And in the reading, it will tell you what X and Y stand for. So note that. Y is the amount of dollars the expected, expenditure, healthcare expenditures per capita, and X is the years after 2000. That's important. So what years after 2000, not since BC or anything, but just since 2000. And then this is the linear equation that defines it. So if we were putting in X is 1, we would be looking at 2001. So if we put in X is 1, times it by 331 and add 5091, it should give us the output of the dollar amount of expenditures in the U.S. in 2001. And we put in X is 2, 2002, so on and so forth. Question A asks us about the year 2010. So based on what we've been saying, X is years after 2000. 2010 means use X is 10. So we're going to solve this equation. It's not as much equation solving as arithmetic if we know the X value and it's all given on that side. I won't have to do any real equation solving, just arithmetic, you might say. So I would type that in my calculator, and that would be it. So 331 times 10 plus 5091, calculator says 8401, and that should be in dollars. Then I could do 2014 and any other year you feel like evaluating, but 2014 would be X is 14, right? So we do it again, Y equals 331 times 14 plus 5091. Let's crunch that on our calculator and check that out. And that comes out to be 9725. So it's going up, right? There's a direct multiplier and then plus a base value that's making it go up a little bit each year. It's going to get more and more, it looks like. Okay, on C, the question is, if the model continues to describe healthcare expenditures, when will the per capita reach 11,000? And we're going to talk about graphing in the next chapter. We would just graph that, and you feel free to go ahead and look at your graph. You could graph that equation and look and see if you get up to 11,000 that way as well. Right now we're just focusing on equation solving, that process, but we can do that. When does it get to 11,000? So we don't know X. You could keep kind of guessing numbers, but the way to do it algebraically would be let the Y equal the 11,000, the output we're looking for, equals the equation 331X plus 5091. Now that is equation solving. So we'll do what we've been doing, more so the equation solving, by throwing that across the line and dividing by the 331 to solve for X. All right, so when we subtract that, we have 11,000 minus 5091, 5909, equals 331X. Then I would divide by what's with my variable, divide by 331, cancel, and that equals 17.9-ish. So what am I going to do with that partial year there? Well, it happens within, even though it's almost at the end of, you might argue it would be 18 if you rounded, right? But we would say it happens within the year 2017, right? At the very end. Maybe it's November or December there, but it's at the very end, and we could figure that out more exactly. But we would say it happens within the year 2017, because that's what 17 means in this modeling equation. All right, so that's what I've got for you for section 1.2. And then you'll work on the homework problems to practice some of these, but I hope this video gives you a good start with that. Best wishes.